introduction. And EUROCAE asked us to do a deep dive on some technical aspects in order to have an interactive session today. So this is what we have prepared for you. So the session will be organized as follows. So there will be two presentations, one from me regarding the update of on the IRP 6983 ED 342 standard for aeronautical products. And we will deep dive into one specific aspect, which is related to the concept of machine learning constituents with, I would say, a compliance standpoint. And then Joseph will present some specific aspects related to the instantiation of this standard to the ATM INS domain. So these two presentations have been done during the previous plenary in April in the US. So you will have the up-to-date information. And after that, after these 40 minutes of presentation, we have planned to have an open discussion with you regarding these topics or any other topics related to this standard. So let's start with the update on the standard. So just a very quick reminder. This standardization effort has started in 2018, so we are 6 years of work, of intensive work. We already published two documents, one which is related to the statement of concerns, which presents the main challenges related to the certification of machine learning-based products, and the second one related to the taxonomy, which presents the main concepts and the useful terms. So we are working now on the main standard. And in terms of updates, the last news that I can give to you, there are two subgroups that have been created in order to manage in the subgroup 8 the human factors considerations in order to go towards level 2, level 3, I would say, applications as per EASA classification, and the subgroup 9, which is related to information security, so the impact of AI on information security. And it could lead to, I would say, a new standard dedicated to AI for related to cybersecurity or information security. This year, there will be also an election on SAE side with a new chair and new co-chair, secretaries, etc. So this process is ongoing, and we will have I would say, the results before the end of the year. In terms of schedule, I will not describe this diagram, quite complex. The only thing that is important is that this year, 2025, is the year of the voting process. So we had a first ballot in March. So we had good results. I think something like 70% of people approved the standard, but we need more because we need a global consensus. And it's normal that the first ballot, I would say, that doesn't pass. It's usual. It's common, sorry. And we have other ballots that are, I would say, planned for this year, 3 ballots with an open consultation here. With an open consultation here from on EUROCAE side. Okay, which will begin in July of this year. So you will receive, if you are part of the EUROCAE members, you will receive an invitation to review the document and provide your comments. Second important information, we expect to publish the standards beginning of next year if everything goes as planned. Okay, so let's deep dive into the MLC constituent concept. So it's important because during the previous plenary in the US, this concept was not well understood by the whole community, and in particular regarding the compliance perspective. So you know that the compliance guys in our organization are persons that I would say knows very well the applicable regulation, knows also what are in the products, and their job is to build an argumentation to be presented to the competent authority in order to convince them that the product can be certified. And these, we had several comments from these compliance experts that it is not so, this concept of MLC is not so obvious for them, and they need, I would say, some clarification, and this is the purpose of this presentation. So it's important to distinguish between two categories of use cases or application. So here on the left-hand side, sorry, it's not the laser. Here on the left-hand side, we have the baseline. So the products are as they are developed today, with traditional system engineering that goes directly to the software or hardware item implementation, following the existing standards. When we move to machine learning, we can distinguish between two classes or two categories of applications. The first category is when machine learning is used to develop a system function. So something that is quite big, that will lead to models that can be quite complex. And that's why you have a new layer of engineering that we have called the ML algorithmic engineering, that is in between the system engineering and the software hardware implementation. And here, the people from the compliance said to us, okay, how can we ensure that this new layer of engineering does not bring issues in the compliance scheme and the way we are doing demonstration today? The second category of application is when the machine learning is used to implement some requirements that are inside the item itself. So I remind for the people that are I would say are not familiar with the concept of item. It's the last level of decomposition of the architecture. When you have a system architecture, the last, I would say, level of decomposition is the item, and from this layer, the item layer, we can choose either the software or hardware implementation. So here we are in the case where machine learning is used to develop some elements inside an item from the item requirement. So we are this second category is linked to small, I would say, small application or simple application with simple models or small models. Okay, so let's deep dive into the first category. And we should first, I would say, acknowledge that the final architecture of the ML model we would like to deploy cannot be known before the end of the learning process. So it is quite unusual for people working on traditional systems, because in general they have a good idea very in early stages of the architecture of what they want to develop. Here in machine learning, it is quite different, since there is a machine that is co-designing with the engineers, I would say the final model, and it's quite hard to have a precise idea about how complex will be the model that will allow to satisfy the intended system function. And here we have an example of an ML constituent that can be one component, one item, other one we can have several items, but that are all either software or hardware, so homogeneous items, and the third case where we have heterogeneous items, so combining software and hardware items. And this, I would say, brings or raises many concerns regarding the compliance perspective, and this is what we want to address. So we have developed a position paper that is available on the SAE website that follows the following methodology. First, we have considered these different case studies, and we have described the system before the application of the new standard, the new ML standards. Then we have described the outcome of the ML standard, and at the end of each analysis, we have described what will be the system after the application of the outcome of the ML standard in order to analyze the interaction between this new layer of ML engineering with the system engineering and show that there is no compliance issue. And for that, we have, I would say, drawn this diagram that shows the execution of the standard by taking into account 3 phases: the initial design, iterations, and the final picture, the final design. So to describe this diagram, we will, I would say, we will describe it step by step. So let's start with the initial state. So here you have on the left-hand side I would say the box where we focus, and on the right-hand side you have the details of what is highlighted on the left-hand side. So here we are focusing on the initial run of the system process. So here you have an example of system architecture where you have several software and hardware items. We have sensors, we have processing of data, and we have something inside the system architecture that will be, I would say, the part of the system architecture that will be developed with machine learning. And imagine the case where the system engineer decides that one software item will be sufficient to implement, I would say, the system function that is foreseen in this architecture. So it's, I would say, analysis. And then we enter into the second step, where system requirements and the system architecture are provided to the machine learning algorithm and the engineering layer. And here you have data scientists, ML engineers that start working, interacting with implementation engineers or software engineers, for instance. And here, after their work, after running iterations of the learning process, they come to the conclusion that one item is not sufficient to implement the function. Let's say, for instance, object detection on images, and they need 4 items in order to, I would say, implement the system function because it is quite complex, etc. So from this iteration of the machine learning process, you have candidate machine learning constituents architecture that are defined by the machine learning engineers. And what is important is that this, in the next iteration, this candidate machine learning constituent architecture should be passed to the system engineering in order to do an impact analysis. Because, as you know, safety is a property of the system. It's not a property of the item, okay? And it is important that the candidate MLC architecture that is, I would say, proposed here, it should be endorsed by the system. And the system will do many analyses in order to show that this proposed architecture does not conflict with, I would say, what has been defined at system level, in particular, safety requirements, but also, I would say, requirements related to the performance of the system, timing constraints, embeddability constraints in a more general way, power, etc. So they will do that. So it's very important that any proposed architecture from the MLC, from the ML engineering layer, go to the engineering, system engineering, for, let's say, validation or endorsement. So let's say that the system engineers approves this proposed architecture. So we will have several iterations of this, I would say, of this work, till reaching the final I would say, N plus N or N plus 1 architecture. And in RP 4754, which is the baseline for system engineering in aviation, the existing text in the version B, the existing text clearly shows that the system architecture is the outcome of an iterative process. There is a concept of final architecture, which is this one. And it is also clearly said that each candidate architecture should follow an impact analysis, including PASA, PSSA, and all safety risk assessment or safety assessment that is known. So this shows that there is no problem of integration of our standard, of our ML engineering layer with existing standard, and there is no, I would say, compliance issue regarding the fact that the architecture of the ML constituent architecture that is part of the system architecture can be delegated to another team and afterwards integrated into the system architecture in order to perform the necessary impact analysis. So at the end of the day, the machine learning engineers proposed an architecture with 5 items in order to satisfy the system function. So we move from 1 item at the very beginning to 5 items, and this will be the real life of I would say, common project in industry. So here you have the final view of what will be the MLC architecture that will be implemented and deployed on the target computer and deployed in operation. And you can see that this part of the system architecture will be, I would say, refined into this one. And this is what we call the ML constituent, actually. So you can see the ML constituent concept as something that designates the items that will be implemented using machine learning and that will need the application of the new standard IP 693 for compliance perspective. So you can see the MLC concept not as a compliance logical, a logical compliance container that designates what will be developed using machine learning. So here you have a detailed view of the final stage, where we have, I would say, an ML constituent that has been, I would say, matured and endorsed by the system layer. And here, in terms of compliance, what we will show is that the requirements that are developed here and the architecture that is developed here will comply with the system requirements, showing that there is a compliance property between them. The implementation requirements that are here, so the software requirement, high-level requirement, low-level requirement, etc., that are developed here, and the source code, etc., will comply with the requirements developed at machine learning level, and therefore, this implementation requirements and the final product will comply to the system requirement through the compliance of the machine learning engineering layer. So it is a two-step compliance layer compared to the one-step compliance layer that is existing today for traditional systems not using machine learning. And this is really what the people from the compliance were looking for, because it was not so obvious by reading the standard, actually. Okay, so now to the question. I see the time. Okay, I have eight minutes. To the question, okay, how do we know that a given processing belongs or not to the machine learning constituents? Because actually it's also not very clear from in the standard what we put inside the MLC and what cannot be in the MLC or is not expected to be in the MLC. So here, to clarify this, there is two questions actually. The first question is, if you have a given processing, let's say, for instance, I don't know, you want to clean your data, or you want to do a specific processing or data processing on your input data. I don't know, normalization. You want to change the images in a certain format, etc. The question is, do you need the insights from the learning process in order to be able to specify your data processing? Because the data processing, cleaning or normalization or whatever, will have some hyperparameters. And if you need the outcome of the learning process in order to specify these hyperparameters and be able at the end of the day to write the requirements specifying this data processing, in this case, this data processing is part of the MLC. If you don't need any insight of the learning process to write the requirements related to your data processing, in this case, you answer no to this first question, and you go to the second question, which is, do you need this processing in order to perform any development assurance activities? So I give you an example, maybe to be more clear on this one. Imagine that you have ML performance requirement that you refine to allocate it to your model. And imagine that you cannot show the satisfaction of this performance requirements by measuring the performance of your model on one cycle. So it is not possible to measure the performance using individual results. You need a sequence of results, so observing the outcome of your model on a time frame, in order to be able to measure the expected performance metric. So you need, for instance, something that do a kind of aggregation of several individual results and compute a global metric showing, for instance, an average or something like that. If you need this aggregation function to measure the performance of your model, therefore, this aggregation function, it is a simple data processing that is not ML-based, it's rule-based, but nevertheless, it is necessary to measure the performance of your ML model, and therefore, this processing is necessary to satisfy one objective of the learning assurance. In this case, if you are in this case, it means that this data processing, for example, the aggregation function, is part of your MLC because you need it for the learning assurance. If it is not the case, if you answer no to the two questions, therefore, your processing is outside the MLC. Saying that it's outside the MLC means that you don't need the standard to certify this data processing. You can certify it using existing standards. Okay, so here it is a summary of what I just said. So the concept of ML constituent designates, if you want a simple definition, ML constituent designates the items of the system architecture that will be subsequently implemented using ML. We have shown through this position paper that you can access. We have shown that there is no impact on the system, the existing system practices. So no impact or no negative impact on the compliance scheme. Here it's a reminder of the two-step compliance, showing that the requirements at the end at the item level will satisfy the system requirement through the ML engineering layer, and that's all. So you will have the slide, so you can read it, I would say, on your side.
Can I make some questions?
Maybe we have a last part of the session where you can ask a question, and then I will go very fast. 2 minutes, okay? In order to present you the second category of use cases. So you remember the second category is a category where machine learning is used to develop simple models that satisfy item requirements and not system requirements. So in this case, the machine learning development process, so the ML algorithm engineering is inside the item development process. So here at the left-hand side, you have a traditional DO 178C process with high-level requirements, software architecture, low-level requirements, source code, and all the verification activities that are described in DO 178C. Well, if you use ML to develop some elements of this item, you will have in parallel the machine learning algorithm engineering, where you will conduct the same activities. You will have to define the ODD, specify the data requirements, design the model, validate the model, etc. So you have two processes that will be run for this item, and what the applicants, so all of us actually, what the applicant will have to do in the internal processes is to optimize the level of the number of artifacts that will be produced. So, for instance, the machine learning implementation architecture that is requested in the IRP 1693 is at the same level of the software architecture. So, do you really need to have two separate documents? I think that there is a room for optimization, and describe the MLC implementation architecture as a subsection of an existing software architecture report, for instance. For the requirements that are developed here in the machine learning process, you will have some requirements that will have exactly the same characteristics as the software HLRs, and others that will have the same characteristics as the software LLRs. So you can also include these new requirements related to machine learning into existing design reports, etc., in terms of optimization. Okay? So it's up to the applicant to define such strategy, as today, I would say. So what is just important to acknowledge here and to see is that it is clear from the committee point of view that the 178C process cannot be used as is to develop the ML part, the ML items. And that's why you have the cohabitation of these two processes inside. Okay, so here it is just a sum up of what I said. So I pass, we'll have the slides. And here you have the final definition of the ML constituents, which is actually exactly what I said before. So you can read it on your own. You will have the slide. It's just a kind of formalization. The new definition clearly highlights the two categories of application: the one where ML is used to develop system function, and the one where ML is used to develop item requirements. Very quickly on the compliance perspective. So I will not have the time, but I will just take 1 minute if Joseph allows me. Thank you. Just maybe to introduce the slides, and after that you can read it, and we can come back to this during the session, the Q&A session if you want. So from a compliance perspective, there are some core certification objectives. So four questions which show what is done today when we want to certify a system, a traditional system without machine learning. So the first question is regarding to the fact that the system performs its intended function and only its intended function, as presented by Juliette the first day, under all foreseeable operating conditions. The second is related to the satisfaction of the safety objectives. The third one is related to the robustness of the system against failures and issues from the operator. And the fourth is the fact that the implementation process is commensurate to the risk. So there is nothing new here regarding what we are doing today for the certification of system objectives. So you should know all of that, so I will not I would say, go into that. So when we are introducing machine learning, we have another question, which is does the behavior of the system that is partly developed with ML is explainable and verifiable, and for that we need other, I would say, compliance mean or assurance means, and this is what will be in green, and this solves the compliance issue that has been raised, I would say, by colleagues in the committee, and I will be, I would say, happy to discuss more of that in the Q&A session. I give the floor to Joseph for the second part.
Thank you. Thank you for coming. I will present you our work done in order to, we have to add an annex in a new standard in order to adapt the new standard and taking into account air traffic management and air navigation service organization context. This work was done by colleague Corinne Gagin from SkyGuide INSP, François Triboulet from IASA, Laurent Plateau, and Loïc Eglinen from DGAC. There's a background. The European Regulation 2017-373 lays down common requirements for of air traffic management, air navigation services, and other air traffic management work function and their oversight. This European regulation introduced to distinguish between two providers. We have air traffic service provider, and we have other than air traffic service provider that we call no ATS. And we have to explain the definition between these two providers. What is the responsibility of each one? For air traffic services, we have to ensure the safety of flight during different process of flight. We have to monitor the airspace situation, have to provide clearance to improve the efficiency of aviation network, and prevent any kind of conflicts in the air and on the ground. Concretely, they can directly interact with the aircraft's aircrew, this is important, and provide information or guidance. And the responsibility for no ATS is to provide supporting services to ATS providers. For example, we have surveillance services, air-ground communication services, and aeronautical information services that are no ATS. None of them directly provide service to crew. You don't have any interaction with crew directly. Now we can specify that there are some service, no ATS services. We have to provide some services to ATS service provider. And no ATS service provider provides service without the knowledge of finite safety performance. This is important, which depend only on ATS provider. Function system and operation procedure. And we have ATS provider apply operational procedures and rely on ATS provider to ensure the proper level of safety. That means for applicant regulators or context, for ATS we have is responsible to certify considering the level of safety they can enter. They have a safety management system, and we have to apply the safety management system in their systems. And we have to change the functional system support safety assessment. We have to support safety assessment to demonstrate maintenance of the safety level. While the no ATS, the safety considering their adherence or the service specification, including service performance. We don't talk about the safety. We can talk only about the performance of services. They do not have any safety management systems, and the change to functional, they have to perform a change to functional system support by safety support assessment. Here we talk about safety support assessment and no safety assessment. We have safety support assessment to demonstrate adherence to service specification. This is the difference between the two providers. Yeah, the goal of this annex is to have an explanation in order to maintain readability and simplicity, because in the core text of the document we don't We don't have any distinction between service and no ATS and no ATS. And we have to clarify in the core document all the term about safety, and we have to clarify this term in this annex in order to clarify the usage of this standard, because this standard will be used by ATS and no ATS. And we have to clarify which difference between these two kind of methodology we have to apply in order to be compliant to this standard. In this annex, we have to provide general consideration on how to interpret safety-related terms on this standard for no ATS provider regulatory standpoint, and we have to apply some more information regarding the core document in order for no ATS in order to apply this standard. That's why in the core document, we have many interpretations, we have many terms. We have many terms regarding the safety term. We have safety critical, safety risk, safety process, safety objective or criteria, acceptable level of safety, safety assessment, safety requirement, derived requirement, safety impact, safety event, functional hazard assessment, and preliminary safety assessment, and system safety assessment. We can provide for 3 examples. For example, for safety critical, for no-ATS provider, this team highlights the need to accurately control the satisfaction of the specification and all associated performance, as any deviation may have consequence on ATS provider using these services. Because we don't talk about safety critical for no-ATS, and for no-ATS, we have to safety critical equivalent to this term. For safety risk, no safety risk is to be considered and managed by no ATS provider. All requirements and design choices are derived from business decision, it's only business decision, and regulatory requirements, and are further formalized in the service specification. We talk here about service specification. As such, when the standard refers to safety risk, no ATS provider or no ATS provider equipment manufacturer should provide risk or not mitigating service specification. We can have the distinction between safety and the services. And for safety process, should read safety assessment process for ATS provider and safety support assessment process for no ATS provider. I hope this is clear for the moment. This is the end of my presentation.
Thank you, Joseph. So now we can enter into the Q&A session. So we have 19 minutes. So any question related to the presentation from Joseph or mine or regarding the standards? Yeah.
So first of all, thank you very much. We'll be all day on that. It was too fast. Just some questions concerning the category 2 that you presented. You had the diagram there. Should we assume that the RTCA 178C development should be in a separated partition from the one which is ML constituted, or can it be all in the same partition?
You mean partitioning in terms of software partitioning? Yes. If you have a safety requirement that requests you that, it's possible.
It's not shell.
But it is not a request from the standard.
Okay.
Yeah. The segregation, the separation between partition or between, I would say, items or either, I would say, item elements, it is something that is driven by safety. So if there is a risk related to that, you will have a safety requirement that will flow down to you, to your development process, and you will have to do that. But the standard does not, I would say, foresee that or request that.
Yeah. Okay. Good. Then this whole process is agnostic to the DAO level. Is it same for DAO A versus for DAO B?
No, we have something that's 74 or 75 objectives that are applicable for DAL C. We do not manage DAL A and DAL B. Okay. And for DAL D, we have, I would say, a leveling that is applied. So I think that you have something that 35 objectives are applicable for DAL D and 75 for DAL C. So there is a proportionality that is in the same spirit as the 138C.
Because my question would be exactly on that part, when it's DAL B and DAL A, which is, you've mentioned the visual object detection, for example.
Yes.
And now my question is, how do you cover all the input data? Imagine if there's code, if there's no code, or can you simulate everything? And also, how credible is your data set? You know, because you can, when you're training the model, you can have a credible data set. The data set itself can be hacked. You can have wrong data, which can somehow influence the model. So the point is, if in the future, do you foresee that even the data sets which are used to train the model should be between brackets certifiable or qualified? So you should have that data set is credible, let's say.
Yeah, you have a learning assurance on the data sets in the same way as you have learning assurance on the model. Okay. So this is what. So you give me the possibility to comment more this slide. Thank you.
Because it was too fast already.
I understand. So here the problem that we have. So what is written in green are here to cover the specific question that is raised by machine learning, which is the fifth question. And actually, this question is mainly here to address this word that is in red. You can see the legend above, which is what is not achievable today in terms of traditional development assurance, what is not achievable for machine learning, due to the fact that all of you know that at the end of the day, when you finish your learning, you have a model that is a kind of design specification that will look like this. It is a technical design specification with mathematical, I would say, operators, weights, internal parameters, etc. And the problem is that, problem that you know very well is that you can no more trace this mathematical operator with the functional requirements. And that's why we are adding all these additional, I would say, activities that we call learning assurance to be aligned with what is in the EASA Conseil paper, in order to mitigate this. Okay? So for your question, the full input space. So actually, from a compliance point of view, it is linked to be able to show that the system performs its intended function under all foreseeable conditions. Okay, this is something that is already asked for any system. It's not specific to ML. In order to, I would say, comply with this, in addition to what we are traditionally doing for a traditional system, we add, for instance, the concept of ODD. Yeah. We also add what is related to the data quality requirements. So data quality requirements will provide you requirements in order to clearly state or specify what means representativity for your use case, what means completeness, sufficiency, etc. And you will do the link with that between the data set and the foreseeable operating conditions. So all what has been added in green is here to, let's say, fill the gaps introduced by machine learning regarding the compliance aspects.
Good. Great. Just one final question on your system architecture of the use case one.
Yes.
The ML components, let's call ML, is it in a separate hardware unit? Because you had FPGAs, processors, and on the MLC there was nothing below. So I was wondering if it uses.
You mean?
No.
Let me go back.
No, but yeah, so on the one, no, on the first one.
This one?
Yeah, if, for example, on the system architecture there, you have FPGAs on top. You have FPGAs, processors, but on the unit of, on that one, that's a separated hardware unit.
Of course. Here we have 5 separate items. Okay? Mixing software items and hardware items. You have software items that will run on CPUs, and your, I would say, some items will be developed using FPGAs, etc. And everything will be part of the system requirement and will have, I would say, dedicated platforms, etc. So here, from this point of view, it's not different from what we are doing today. When you have a complex system function, you can implement it into a combination of software and hardware items.
Which is considering CPUs and FPGAs, not GPUs.
You can, if it is your use case, you will have maybe more challenges for certifying the GPUs, but it will be up to you to manage that.
To the client also. Great, thank you very much.
Thank you. Yeah.
So I have a question on the things in green. So which of them will cover data set poisoning?
Data set poisoning, good point. I will just show the green so that we can maybe discuss. But data set poisoning is related to, I would say, intended malicious attacks. Okay, and it is so short answer. Our standard does not include, I would say, information security aspects. It's a standard that is dedicated to safety. And that's why at the very beginning, I have said that there is a subgroup, which is subgroup 9, that will, I would say, work on what should be added in order to take into account information security.
Okay.
We still have 10 minutes. So maybe just in the meantime, in order to maybe to think about questions. Well, we have discussed about the learning assurance that is here. For the second aspect, for the second question, which is related to satisfaction of safety objectives, there is something that is quite important, which is the possibility to refine system requirements that give you an overall objectives of performance for your for the part of the system that will be implemented with ML. And the fact that we are able to link these performance objectives, which will be described using performance criteria, metrics, etc., to link it with the performance criteria and metric that we are using at the model level. Because at the model level, data scientists, ML engineers are used to use, I would say, specific metrics related to confusion matrix, the IOU, MAP for the object detection, and things like that. And there is really a challenge to link these data science, I would say, metrics with, I would say, performance objectives that are expressed at system level using functional point of view. So here there is a real work to be done, a real engineering work to be done that should, I would say, involve both system engineers and machine learning engineers. And sometimes it is not possible to refine these system performance objective at the boundaries of the model. You will need to add some steps or some processings in order to be able to measure something. So for instance, if you have performance objectives that tells you something like, I have maybe an example that is good. That is maybe just before. Yeah, this one, for instance. Take this requirement. It is on object detection. So the requirement says, the first one, while tracking the movement of detected objects on images containing unintended objects, the MLC shall minimize the creation of false tracks. So this one, to measure it and to satisfy it by having only individual measuring performance metrics on individual cycle, it could be just impossible. You will need a sequence of several applicative cycles, so a sequence of, I would say, of inference, in order to be able to measure something on a time frame that will be representative of the functionality that we have here. Same for the second one. While tracking the movement of detected objects on images, containing partial object occultation and movement crossing, the MLC shall accurately maintain the association. You need to be able to measure that, you need several images. You cannot compute any metric on single images. You need a sequence of images. And with the sequence of images, you will have to aggregate individual results in order to compute a global metric that will allow you to measure the performance of your MLC on this sequence of events. So you will need test-based scenarios, actually. Scenario-based testing. Okay, so that's important to have this in mind, because sometimes it is just not possible to satisfy all the requirements, and in particular performance requirements. At the boundaries of the model, you need more than that, and that's why the ML constituent concept is very important for that. Also, sometimes you cannot satisfy the performance requirement or the safety requirements just with the MLC. You will need to add some runtime monitoring in order to mitigate some risk that your model cannot manage very well. So all of that is foreseen in the standard. Regarding the robustness to failures and misuse, I will not detail all of what is there, but there is something that is important in the standard, which has been improved in the draft 6. So I invite you to read the draft 6. It is what we call the verification of verification. And in particular, we have added in the verification of verification a part which is linked to the use of explainability methods in order to track, detect, and mitigate unintended behavior. What I mean by unintended behavior is the fact that your model is sensitive to information that are not really linked to your intended function. So, for instance, the background of the images or things like that. And there is a section that details how it is intended to use these explainability methods to, I would say, to satisfy the compliance objectives linked to we don't want unintended behavior. Okay, and this is, I think, an important improvement that I highlight here just for your knowledge. So for the rest, I think it is quite. So the last one is the proportionality. So we have, as I said, for DALD, a part of the objectives that are applicable. For DALC, all the objectives are applicable, and the future issue of the standard. So in 2026, 2027, etc., will try to, I would say, address more critical applications. But I think that we will need some feedback from the industry, from the application of the first issue of the standard, to be able to go towards DAL B and DAL A. I look to Juliette for that, but I think, yeah, we need some experience and feedbacks for dealing with very high critical, I would say, applications. So.
Maybe for more automation, like not. Maybe the next version of Zosa will be applied for system with more automation. Yes. Not more automation.
So 3 minutes. 2 questions. Good.
Yeah, Fateh, regarding the answer you gave to the previous question on, information security risks, to me, this referring to system misuse opens it to potentially intentional or non-intentional misuse. But how do you actually separate things between an intentional misuse that is in fact an attack, and that falls potentially in the case of information security risk, and non-intentional misuse that can be exactly the same act but with a different intention.
I understand. So the fact that the system should be robust to failures and misuse, it is something that is existing today in aviation for traditional systems. So, for instance, a misuse can be due in airborne for air crew or air traffic controllers, can be due to for instance, the fatigue. And there are some specific assessments that are done in order to track this potential misuse, or the fact that, okay, due to the fatigue, the operator will interpret things, I would say, in the wrong way, etc. There are specific assessments and specific mitigation means that are, I would say, that are done in order to manage that. For what is intentional, it is another type of assessment, and you know it very well, because managing attacks and what can be done by, I would say, attackers, and there are different levels of attackers, you know this very well, far better than me, require a specific security risk assessment with specific methodologies, with specific security control, specific, etc. And this really needs to be studied and investigated as a whole, and we cannot, I would say, just because we have things that could be useful, say that we are addressing cybersecurity. It's not true. To address information security, we need really to investigate all the problems, and I think that there will be another standard. There is something that could be interesting, which is adversarial attacks. So sometimes we generate adversarial samples, let's say, adversarial samples. We generate adversarial samples in order to robustify the models, but for a safety perspective. So we are using exactly the same techniques, black box, white box, in order to find the adversarial examples that maximize the error between the prediction and the ground truth. But we should be very careful about that, because generating adversarial samples that are not linked to the intended function could generate on the model some unintended behavior. This is it is the same as oversampling. When you are oversampling your data set because you want to add robustness, oversampling the data set can change the weights of your model and can introduce, I would say, some biases that you do not expect. So it's the same for adversarial attacks. So that's why we should also be careful about that. Thank you very much. I think we have to close the meeting. Is there, maybe there was a question, but we can discuss. You want to ask it?
Yeah, it's just a short one. You explained some supporting processes for the LLC, like the data preparation process, or is it all mapped into the standards?
Yes. Yeah, absolutely. Yeah. Yeah. So I think it's quite detailed. Some people in the committee think that the standard is too detailed, but it is because we have added, I would say, what we think useful information regarding all these steps and all these activities. So I would be happy to answer, to discuss more about that if you want. Okay, thank you very much.
Yeah.
C'est bien votre présentation?
Oui, c'est bon.
Okay, parfait. Yeah, I hope everything is okay for the sound as well. Okay, so it's my pleasure to follow on with several panelists after this nice presentation from Fateh and Joseph. So there is it's really a follow-up. So the topic will be about Trustworthy AI toolbox. So Fateh presented these green items, which are these new requirements which are linked to the learning assurance. And what we will present is our proposal to answer some of the objectives and to propose some new means of compliance at some point that can be used on the way to provide evidence for the certification along the new standard. So my name is Romaric Redon. I am the operational director of ANITI. ANITI is one of the 9 AI clusters in France, and it's a center of excellence for development of trustworthy AI based in Toulouse, federating all AI research, innovation, and education activities in Toulouse. So, for example, with ENAC and SUPAERO that you may know. Yeah, some words about myself. So I've been working 26 years on innovation with AI for aviation. So I'm not new in this domain. I was previously managing the AI roadmap in Airbus, and now I am appointed to be the operational director of ANITI. And there will be several panelists during the talk that I will introduce now. And then I will invite you to join. Maybe I don't know if it's good now because you may have the live. No, it's okay. So you may be able to come. So I will call them in the order of the presentation. So we will have first Vincent Musso, who is from IRT Saint-Exupéry. Yeah, I think you can come. So Vincent is a research engineer in the DEAL integrative program, and he will describe what we are doing in this integrative program. We will have Jules Tevison from Thales, who is a data scientist. So I saw Jules, yeah, you can come, who will give some testimony on some of the library which we have developed, and Jules has used this library. We will have Stéphane Grillon from Airbus. Stéphane Grillon is an AI expert in airframe. And he will also provide some testimony on some of the library. And finally, we will have Juliette Mattioli, who is an AI fellow in Thales. You had the pleasure to listen to her yesterday. And she will give also a view on how we go from these libraries that we have developed mostly for data scientists, but how we can really use them for industry and promote, deploy them, maintain them, support them. And this is part of what we are pushing with the European Trustworthy Foundation, and Juliette will give more information. So then we will have some questions, and I will make a short conclusion before we move to the Europa room, where we are expected at 4. This is what I've been told. So mostly we can start with the presentation of Vincent to set the scene. And yeah, I leave you the floor. Yeah. Yeah. Yeah, you don't. Après, je savais pas si. Okay.
As you want. Okay. Okay. So hi everyone. I'm Vincent Musso from IRT from the DEAL project. I will present you how we approach the question around certification and the means of compliance that we can have on several topics of interest, like robustness, explainability, and so on. So I will explain you how we developed a sort of toolbox, a set of libraries that can be applied on specific use cases. And I have specific use case I will present you as well. So as you all you are all familiar with that, the AI Act is entered in force. There are several papers and norms that are arriving, like the one we just saw 1 hour earlier. We have other norms in other domains like railway or automotive as well. And we have this learning assurance from EASA, where there are requirements expressed and there are objectives, high-level objectives. And our question is, how do we apply this to a typical ML lifecycle? So if you take the typical ML lifecycle, you have a training set, you train a model, you have typically a neural network. We work with neural network mostly, so I will talk about this, but it might be applied to more than that. And then you have unseen data, you have inference, and you try to make prediction. There are plenty of questions that can arise: relevance, representativeness of the data set itself, biases potentially, good biases and bad biases, obviously. And there are also other questions at other steps of this chain, like performance guarantees, robustness, transparency, explainability, and so on, generalization capability. So we need a way to address all these questions. So, but to do so, we wanted to have something that is more than MNIST or CIFAR 10, if you are familiar with these, which are typical academic use case data set, and we wanted to work on something a bit more closer to industry. So we worked on a specific use case, which is LARD, which is based on the detection of runway during landing. So our task is simply to detect the four corners or the bounding box. We focused on this first step that was also maybe presented yesterday by Daidelen. It's the same type of architecture. And for this task, we want to be able to detect the runway because we want potentially at the end to compute our own position with respect to the runway to be able to allow for an autonomous landing. So this is based partially on machine learning at some point, and the stage of runway detection is machine learning. The task looks like that, and what we did first was to try to see what was given in terms of ODD definition in the IRP and try to apply it to the creation of this data set to build something from the ground, which would already satisfy the requirements expressed in the IRP. And to do so, we define a specific operational design domain. We try to define it formally as much as possible, and we published a paper on this topic if you're interested. And then we added a few more important factors. This was only the position inside of the aircraft with respect to the runway. And we also added a few more parameters, which are typically the type of runway we may support. So we wanted to support mostly commercial runways. So we focused on runways with a piano, with the landing stripes, the stripes you can see, which look like a piano. So these are the types of things we added to the operational design domain to further restrict the task and identify really the smallest domain we could think of and could define formally. So then we used the synthetic image generator and we produced a large data set of 70,000 images from various runways, and we have something to work with now. And we have also a real image to compare, which would be more representative of the reality, the inference time. This was the first version of the LARD dataset last year, and we are currently working on the second version. Since we have a scenario generator, we can generate a position against a specific runway in the world, anywhere in the world, and we can generate images. So we have currently, we are building a second version with 150,000 images, and which would be also multi-source with flight simulator explain with a lot more variability. So this is our starting point. We have a use case which is well defined, which follows. This also we applied some verification of data quality requirements as you just discussed, and we have also a paper which try to follow the expression of these data quality requirements as requested by the IRP and the verification of these requirements. So this was our first step. So this is a bit of some variety in the training and the test set. And what the video is not great. We might see some detection. Yeah, okay. So here we have a simple YOLO model that was trained on the synthetic images, which were generated from Google Earth, and then is applied in real world from an aircraft where we are really landing in Tarbes, I think. So the model is really good, even if he was only trained on synthetic images. But there are also two detections on the left. As you can see, the circles are considered as runway by the YOLO. We don't know why. This is where we might need some additional tool to explain this decision, to maybe mitigate the problem that can occur. We have also some detection on the right of the planes here. So for this, we may have new methods to apply. So if we look at the whole requirements from the learning assurance, we try to identify the main topic, the main challenge that arise from in the whole chain. So, and we have specific teams in our institute which work on each of these topics. So we have one team per topic. So one team explainability, one team robustness, fairness, and statistic quantification, and OOD detection. And we have new other ones, but these are the main ones. And we are trying to answer the question: how can we identify means of compliance, how to choose the right methods, because the state of the art is ever increasing in each of these domains, and there is plenty of answers from the researcher domain, but maybe some of them or most of them are not applicable, are not usable by the industry. And the other question we can ask, we are also working with people from the WG as well, and from EASA. We make return to them, we make reviews and so on, and we try to come up with ways to include what we do in the EASA concept paper, in the WG and so on. So if we take the big picture again, we have a first libraries that we developed. So each challenge, each team worked on a specific library as well. So we built open source libraries. So this one allows to detect biases in data sets, so we can apply it to training sets. And usually we need the model as well to obtain some insight about the training set. Then we have some robustness, which is by design here. So we have a specific library for that. I will detail each of them later. Then if we look at the rest of the typical pipeline, we have explainability, which is important and even referred in the AI Act. We have detection of OOD, out of distribution, that is really close as well with operational design domain, that can be linked with that, but not exactly the same. And we have also conformal prediction that can be applied at the end on the predictions themselves. So this is a big picture, and I will start with, since we need a model, I will start with robustness here, because the library we have, one of the library we have works on robustness by design. And when I talk about robustness, I talk about adversarial robustness here. So it's mostly attacks linked with adversarial attacks that most of you may know. Here we are in a context of object detection, so it's pretty specific. We have one class only, so the type of attack we can have is either build fabrication attack, where we fool the model into thinking there are other runways in the picture, and the other type of attack is vanishing attack, where we transform slightly the image again to make the runway disappear from the picture. These are the two types of attacks. We are not interested in this in terms of cybersecurity. It's only a representation of the brittleness of the model itself, and can be seen as a way of typical natural perturbation could lead to that type of problem in the model. So for that, we have a specific library, which is, as all the one I will present, pretty easy to use. It's only small changes against existing libraries, and we can obtain, for a specific architecture, a given architecture, we can obtain a Lipschitz model. I won't dive into the detail here, that's not the idea, but if we look at the result of this process, we obtain a model that can be robust. So here, on the top right, we have a classical model that is easily fooled. If we look at what's needed to transform the image and make the runway, new runways appear, it's really not visible. While if we look at a robust network, we can see, I will zoom a bit, but we can see that the perturbation needed to be able to fool the model, to make him think there is a runway where there wasn't, really start to look like something that is a runway for the human eye. So it's really what the idea behind the Lipschitz robustness. And if I do the same for the vanishing attack, so making the runway disappear, if I look on the top, it's easy to make the runway disappear with a normal model. At the bottom, for a robust model, Lipschitz model, is way harder, and we have to change, really add a perturbation that modifies the image that will make the human believe there might be something wrong here. So in technical term, it really needs an epsilon large perturbation radius to be able to fool this model. So once we have a model, we can start looking for biases, and for that we have another library which is also open source, which is Influencer. There are plenty of methods. Obviously, I won't dive into all of them, but and you can check all of these at the end. There are QR code you will see, and for this one, I will just show you a clustering, an example of clustering, which is where we try to find features, and with this feature, we try to make a partition of the training set, typically, and once we have a partition, we try to look at each of the element of this set of image in each partition and try to find some insight about the data set and find biases. So for example, here we have color clustering that was applied, and if you look, and these are the performance of the model for each clusters that we defined. And if you look closely, you can see that the second cluster, the cluster 2 in green here, is really has really poor performance. Has a recall of 0.5, something like that, and average precision as well. So it's really low compared to all the other clusters. And what we saw is the cluster 2 looks like that. So the image in the cluster 2 are really image of sound around a runway, which is really clear. So the separation between the runway and the ground is really not that clear. It's hard to find. So it seems like if we want the model to behave better in this type of environment, we need to put more data in in this style. And on the other way, on the other side, we have the cluster 5, which has almost perfect accurate average precision and recall. And what we saw is the cluster 5 contains this type of images where the runway is really extremely visible, extremely different from the side, has clear markings everywhere. So these were the type of insights that we could obtain with the bias analysis. So now that we have seen some bias, we can check the out of distribution part, where we also have a library which is OODIL this time. And if we look at the result from the YOLO trained on synthetic images, on real images, this is what we obtain. So plenty of false detection everywhere, especially the cockpit itself is a problem. So what we did is we used, so the runway is in the middle, just to be clear. There are often detection on the runway, it's correct, but there are also a lot of false positive everywhere. It's really a problem. So we have the OODIL library, which allows to dive into the detection of OOD. I won't dive into the details. I think I may have time. All the points you have here are detection by the model. They are all, and if we don't consider the threshold at all, these are all the detection on all the pictures by the model we applied on the real test set. On the left, you have a third threshold, which is the threshold of the model itself. So it thinks like this box, the box who are below 0.25 are not considered as box. We consider that these are wrong detection, so we will discard them. The model will discard them automatically. We can change the threshold if we want. But if you look closely on the top, the yellow one, for example, are the correct detection. So as long as we continue moving the yellow line to the right, we will lose a lot of correct detections. This would be a problem. On the bottom, what we have is the another threshold, which is this time OOD detection, is based on OODIL, which defines another dimension through which we can remove a big part of false positive as well. So what we did is what we can do is move this threshold from bottom to top this time and remove a lot of the false positive, and in the process we remove only a few red points which were correct detection. So this is the idea behind OOD detection. We can try to decompose the space into a second dimension and more if needed, to try to remove more false detection if needed. And the result look like that. So I'm not sure it's visible. Okay. The cyan box were detected as OOD and were removed in the process. So most of the time on the bottom right, for example, we removed the second detection, which was really wrong. There are still a lot of false positive, and also sometimes we removed, sadly, the correct detection. For example, on the top in the middle, we have a detection which was correct that was removed due to the OOD detector. So these are still to be tuned, and we could combine several approaches, which we didn't do yet, but this can be used as such. Then we can obtain some guarantees on bounding box using conformal prediction or quantification of uncertainty. And to do so, we have a library which is Punk. In this case, we applied it on the correct, to fully enclose the ground truth. So what we wanted is to be sure to have the ground truth entirely in the box predicted and not just overlapping at some point. And as a result, we need a calibration set to do so. We add that was fine because we have generators, synthetic generators, so we can build make new images and new labelization if needed. And then this is what we obtain, this type of images. Here, what we say is we ask for a 90% guarantee to have the ground truth enclosed in the green box. The initial detection was the red box, maybe, I am not quite sure. But one of these is not correct, and the blue one is the detection, sorry. The red one was the ground truth, and we wanted to be sure to have the ground truth enclosed. So using this, we can obtain this guarantee of 90%. It means that in 90% of the case, we are sure to contain this, to have the bounding box inside the green box here. And then finally, we might want to explain the decision, and to do so this is another library we have, which is Explic. And in Explic, we have typical attribution methods, which you might have seen. So there are plenty of methods in the state-of-the-art, as always. As in the other library, there are also all the state-of-the-art methods. So these are all available directly in the library. You can use any of them, but clearly, there are some issues because all of them should be used by someone, interpreted by someone afterwards. But here you have different results from different methods. You might not be sure which one to use. We tried to use them on LART to see what we could identify with that. So this is the type of result we obtain. So depending on the method, we have different type of answers. So some might be more satisfying than others. On the bottom left, we might have something that is more interesting, more interpretable, but is still open to interpretation. The model seems to look a lot at the bottom left of the runway, and maybe he looks at the horizon to find the end of the runway. It might be an interpretation, but it's hard to understand if it will help or not. We have also plenty of parameters we can play with. So this is another problem, I would say. And finally, yeah, we'll skip that. No, I won't skip. I think I have time. And finally, we can explain not only true positive, but also false positive. And if we just come back to, I just said at the start that we used Lipschitz network, which use robustness by design. So we built a model that was robust by design. On the right, you have this model. On the left is a classical model, non-robust model. What we saw is the Lipschitz model are more interpretable by definition, by construction. And on the right, what we could see is that for false positive, which was present for the same image by both models, we saw that on the right we have some lines starting to appear, which may help us understand why this was considered as a runway, while on the left is just blobs of points, so we cannot really interpret anything. So this was one of the insights we could have. And currently we are working on another method we have developed in our project, which is based on concepts. So the idea is just not to look where the model is looking and to explain if the model looks here, but what is he looking at. And the idea is to automatically extract a group of concepts. For those who went to the presentation, I had a presentation about that on the demo. And here we have, for example, a set of a detection which could correspond to the piano itself. You may have a part which is more the horizon, focused on the horizon, and you have the surroundings as well. This might be a problem because if the model looks at the surrounding to define what is the runway, it might use some biased information. So this should be maybe investigated. But it's a type of method that we think is more interesting and go deeper in the explanation than the simple attribution maps. Okay, so and just to conclude, so this is the whole picture. Everything is available on the GitHub. Just to final addition, we have a very new library we just come up last week or 2 weeks ago. So this was not included in the slide yet, but it's about formal verification of neural networks. So for those interested, it's also part of robustness and adversarial robustness. But yeah, thank you. Thank you. Any question?
Thank you, Vincent. I want so it was said by Vincent. So these are open source library. I would add the point that they are with MIT license, which means they are non-contaminating library. So you can really use them on your project. This is one of the objectives for you to be really early users of this library. And now we will go with some of these early users. So we will start with the testimony of Jules, who has been working with the DIL LEAP library on a use case. So I let you continue, Jules. I will just put your slide on the screen.
Yeah, thank you. So I will be really quick. I only have one slide. So we used DIL LEAP for one of our use cases that I presented just this morning. So this is Top Sky Sequencer. So just as a reminder, it's an AMAN demand, so Arrival Manager, Departure Manager. And the neural networks that we are training are predicting the time to touchdown, so the estimated time of arrival of aircrafts. And the input data basically is the latitude, the longitude, altitude, the aircraft type, and the heading, and the ground speed as well. And the output is the estimated time of arrival, plus also a confidence interval that we compute. So we use a special loss, which is called quantile loss. But we tried for this we use DLIP only for the output of the estimated time of arrival. So DLIP is a library that implements some a type of normalization, which is called spectral normalization, in order to ensure a constant, which is called the Lipschitz constant, sorry. And this constant says that if your neural network is Lipschitzian, it means that if you change the input of your neural network, the output will not change by a constant multiplied by the delta of your input. So that's a quite nice property. In some cases, you always have a constant that allows you to, how do I say that? Yeah, what I mean is that your constant has to be found. You have to define what is the right constant for you, because according to the train set or even the test set, the problem that you want to solve, this constant can be higher or lower. So if you constrain your neural network too much, you will have a decrease in performances. And on the contrary, if you have no constraints on your neural network, you will have maximum performances maybe, but you will not have the good property of C-Lipschitzian neural network. So that's what we did. You have, I think, different techniques or methods to find the right constant for you. One basic method is just to train different neural networks and look at the trade-off that is best for you between performances and stability of your neural networks. So for us, I have a little plot on the right. And as you can see, you have on the two axes the output deviation and the input distance. So input distance is a perturbation on the input of the neural network. And the output deviation is the deviation that we observe as on the output of the neural network. So if you have some points on the top left of the plot, it means that you have a little perturbation and a big impact on the output of the neural network. So it means that your AI is maybe not really stable. And on the contrary, if you have some points on the bottom right of the plot, it means that you have a lot of perturbation and little impact on the output, which doesn't mean that it's good, but it means that your neural network is stable. You have all the points here in blue for the original initial model that we used at the moment. And in red, the new model that have been trained using the DLIP library. And what we can see is that we have more stability because in average, all red dots are above, under the line, the red line here. So that means that our neural network is more stable. And also, I didn't show the performance metrics, but they are exactly the same. So we have, not exactly, I think it's 0.2%, maybe less accurate, which is not a problem for us at all. And we benefit from the stability, better stability on the output of our neural network. So yeah, basically you have to fine-tune a little bit your constant to find the right one. And if you manage to do that, you will have benefits from the library, I think. For further improvement, it would be nice, I think, to be able to have different constants, C-Lipschitz constants, according to the input variables. And maybe also it could be interesting to be able to have different constants according to the region. Just an example for us, sometimes you have arrival procedures, and if the aircraft or the flight is going a little bit on the left or on the right, maybe on these particular cases, we need an increase or more important constant, Lipschitz constant. And for the rest of the cases, maybe we don't need this. So yeah, just some details, but in average, it's completely fine for us, and we are using it now.
Thank you, Jules, and thank you also for the feedbacks in order to improve it, because we are also welcoming not only these feedbacks for us to improve, but also contribution to improve these libraries, because we have external contributor. So now I will leave the floor to Stéphane to give another testimony. Also, the topic of stability will be discussed. So it's linked to the Decommon library.
Yeah, I call that a battle of methods. You will understand when you will see the little picture or icon representing Decommon. I would like to talk about generalization and stability, trying to demystify a bit what generalization is and what are the methods we need to do a generalization. There are two, in fact, I understand that thanks to the MLIP report. There are, in fact, two considerations of generalization. There is an a priori generalization when you don't know yet the model you want to build. And there is a posteriori generalization when you have already built your model. And this is the second one, which is really important for verification and to ensure the famous quantified generalization guarantee requested in the ESA concept paper. And the second way is much easier than the first one, because in the first one, you have theoretical bounds like you can find in the Codan report, giving you, in fact, an idea of the generalization gap or of its upper bound for a family of models. And this kind of inequality are intended to select the right models and to select also the right numbers of training, and in some papers also of the validation data set. But in fact, these are recommendations. So we are not there in methods that can be used for verification. This is just to give you the right guidelines for your development or your validation. So what we have to focus on is what I presented yesterday, a posteriori generalization by using this probably acceptably correct approach. So this probability of error. So here the probability that the error is less than epsilon is greater than 1 minus delta, and I materialize the interval here, which in fact insists on the fact that it is also a confidence interval, a global confidence interval. And this is totally equivalent to a bound, an upper bound on a quantile of index 1 minus delta, with delta being the risk. So, and for that, to ensure this kind of inequality, we have statistical theorem, we have the Wilks method, particularly, that can be used. There are some variants, like the Wilson score, but the Wilks method is based on the binomial distribution of this inequality. And you have a simple inequality to ensure, to give you, in fact, a good estimate of this upper bound. And this, for this, you just have to take, you just have to sort your errors for your verification data set and take this rank here, n times 1 minus delta plus petit n, being a margin to ensure a certain confidence in the estimate of this upper bound. So it can be found, this kind of approaches, in the OpenTerms library, which is a statistical open source library. You can find it, and you can do your own generalization proof, just ensuring that you have enough test data to ensure this, this bound. And typically, if you need a 95% confidence interval for a 90% level of error, 30 samples can be enough. So, of course, your verification data set has to be large enough, so with n and representative of a certain distribution that is translating your model intent.
In fact, the distribution you have to follow is not necessary when you do machine learning, the operational distribution. We saw that yesterday in different presentations. They say, I want to weigh some samples in order to insist on what is important for my model. So weighing a sample is like changing the distribution, resampling the distribution in such a way, doing important sampling in such a way you can orient the model in the right way. So again, a posteriori method, so this is why I'm talking about demythification, is just about statistical estimates. And second, other topic is about the stability. So the stability consists in proving that little perturbation on the input gives little perturbation on the outputs. And for that, we have used two families of methods. We have based on decommon, so this is the icon, which is a formal method. This is based on upper bounds, cumulated upper bounds across neural network with some convexification of the activation function. So it's working quite well. We have an example here on this plot where we used decommon and we compared with the statistical approach, the Monte Carlo approach, for a linear model. So it looks very close. However, in some cases, in some non-linear cases, we found some difficulties. So I know that there were some improvements of decommon in the recent months. I need to test. But for the time being, we still keep the statistical approach for doing some comparisons every time we start a new project. And I would like to take some distance also with respect to this statistical, with respect to the stability objective, because stability cannot be verified in many cases by your ground truth. I have taken here two classical aircraft engineering problems. The distribution of pressure for wing airfoil. You can see here that the distribution is not regular at all. It is even, you have very steep slopes there, and so the ground truth is not stable. Same for the change of structural failure mode in my domain, in airframe engineering. You can have switches from local buckling to global buckling, which are discontinuous in some cases. So again, there the ground truth is not stable. So the model will not be stable. So we have to take the stability objective, whatever it comes from, concept paper or standard, with a lot of care. Because sometimes you want to be accurate, especially if you want to predict the shock wave for a wing. You have to reproduce the discontinuity, so you have not to be stable around this shock. Okay, so stability sometimes will be contradictory with the accuracy. So that's all on my side.
Thank you, Stéphane. So I think it was a very good point. We've seen that also previously. I think it was a point Fateh made, the robustness aspect. I mean, no, Fateh and also Jules, you mentioned it. It's always a trade-off between some of the attributes that we want to have. We cannot get all of them at the same time. So you might want something which is more accurate but less robust, or more robust but less accurate. In the specific talk that Stéphane did, it was the trade-off to find with stability. On all these tools, that's why we call it a toolbox, because they come all together. They don't come as a single answer. You have to use a bit of all of them to find the right trade-off to answer the standard objective. And also, you need to be somehow accompanied to get some support in the usage of these tools. And this is a transition to what Juliette will speak about. I mean, how you go from this set of tools from data scientists to something which could be really used enterprise-wide, I would say, and also linked to more our global engineering processes. So I will just switch to your slide. I think that's the first one.
So first of all, as you see in my previous talk, if we want to deploy AI in a responsible way or in a trustworthiness way, we have to provide some methods and tools for AI engineering. And the aim of all projects that we mention, especially DEAL, but also Confiance.ai, aims to address this problem. So Confiance.ai was a project which aimed to capitalize all methods and existing methods and tools, and sometimes to add some new methods and tools. So there is today what we call a catalog, where you can find all the mentioned tools already. So it's very easy to find it. You Google it, typing Confiance.ai and the catalog, and you have all the list. But now we have to go to another step in order to be sure that all these kind of tools and methods will be industrialized and also update during the overall life cycle of our systems. So it's a kind of way to address in the overall life cycle, these kind of things. So we decided with all partners of Confiance.ai, where Anity, especially ERT Saint-Exupéry, was involved, but also Airbus, Thales, and other industrial partners. We decided to set up a foundation called the European Trustworthy AI Foundation in order to first animate the community of all people who have the same concern, to also integrate all methods and tools, and to industrialize it in order to offer to industrial a toolbox or something like that. And it's very convenient for an industrial to have all tools in the same place. So the Trustworthy AI Foundation will be officially launched during the summer. If you want comment tu fais celui-là. So today there are some membership. So you see that there are some industry coming from defense, but also coming from other discipline and other verticals. There are people coming from research, such as Saint-Exupéry, and also some other issue. Then we enlarge the foundation in order to have some the ecosystem with a lot of startups. Some are dedicated, for example, Kili for labeling, how to label your data and to have a good quality of labeling. And today we have this member. So just to have a first advertisement, we will set up a first day called the AI, the Trustworthy AI Summit on September near Paris, in Saclay. And this day will be dedicated to officially kick off the foundation, but also to provide some new catalogs, some new methods, and so on. So please.
Thank you, Juliette. So first of all, I would like to ask you to give a warm set of applause for the speaker. And we have time for some quick questions. I would like to keep 1 minute for wrap up at the end, but if you have any questions, it's time to raise them to me or to any of the panelists. Yeah? Sure.
Yes, so Arthur Clavier, Currency Aerospace. Thank you for the great presentations and the many capabilities you showcase, which I think are definitely relevant for AI trustworthiness. My question is about qualification of this toolbox, because at the end we need also to trust those tools which we use to build trust into AI, and so there are a couple of tools in the literature that have some dependencies on many, let's say, mathematical optimization libraries, for instance. So have you investigated this topic of the qualification of these tools, and do you see any obstacle to this qualification?
So it's a known topic because if I take the example of the formal verification, I mean, we already use in aviation formal verification, not for neural networks, but for other topics. And we have had to qualify these tools. So the aspect of qualifying the tool chain is a known process. It's an ongoing discussion, especially with EASA. And this is part of what we are discussing on the rule-making task. I'm part of the rule-making task with EASA. What level of requirements we will put on the qualification on all of these tools. That's ongoing discussion, but it's clearly something we have in mind. Making links to scientific research, that's the good aspect which we have not presented here, is that we have the libraries on one side, but also we have really the scientific papers which are underlying these tools, which, by the way, have been published to the best machine learning conferences. So we have the solid background to provide evidence on the scientific aspect, yet it's something which is to be done.
Thanks.
So I would have a question for Vincent related to the cyber attacks that might be directed at the models, at the object detection models. So you basically said that it is at a certain point the cyber attacks are visible to the human because the perturbations are so high that, for instance, it's actually visible for a human to see. Possible for a human to see that there wasn't a runway and then there isn't a runway. But are you actually thinking about building the possibility of recognition that there wasn't a runway and now there is a runway into the model to embed that type of logical reasoning into the model itself? Because if you're thinking about fully automation, it means that you will not have a human to actually check that there is a runway and then there is not anymore a runway.
Yeah, okay. So you mean more on the monitoring side? Monitoring if there is something wrong happening. This can be done, but for now we have specific papers that looks at this topic, and the conclusion was that monitoring this type of thing is not useful. It reduces a lot it's not useful. It reduces a lot the availability of the results, while it doesn't increase that much the robustness of the overall system. What I'm showing here is mostly the fact that the robustness is representative of the brittleness, and this is the important part. We don't expect to have cyber attacks on the model images. If someone is able to take control of what's happening in between, it will remove the image. It won't start trying to build a complex system to evade or change the images slightly to be sure the human, the expert doesn't notice. But it's not really the point. The point is really looking at this problem as the model is robust, and if we want to fool it, we need to go really far in terms of perturbation. What it shows is if you consider the perturbation as the brightness problem, typically, or rain on the windshield, typically, it means that Lipschitz model will be resilient, will be robust to more rain on the windshield than a normal model. This is really what we are trying to explain here.
Thank you. Yeah, last question.
quick question for Vincent or Jules also. Thanks a lot for the presentations, really nice. I have just a question on how much increase in compute or training time does this involve? Because also, and do you see this as a limitation for the adoption of these tools? Because there's maybe not free lunch for. Thanks.
Yeah. No, in terms of computation, it's I don't have the exact figures in mind, but so stop me if I'm saying. But in my, I think it was a little bit longer, but it was like maybe 10 or 20%, not much. So for us, it was nothing because those are little neural networks, so we train them in matter of maybe 1 or 2 hours. So I don't see any reason not to use DLLIP. So that's a reason why we tested it. It's really easy to implement. You just have to add spectral normalization in your neural networks. It is compatible by design with TensorFlow. Yeah, TensorFlow. Yeah, and PyTorch. Both. No,
there are 2 separate levels.
Okay, so at the moment we tested it, it was, I think there was only the TensorFlow implementation. So now also PyTorch. So yeah, really easy to use. Then I think we just said that the main thing to do is to define your trade-off between stability and accuracy, and also check if you have some discontinuity in maybe some discontinuity that you want to have in your neural network or not. So yeah, and that's also maybe something that could be added in the future to have the possibility to ensure this constant, this Lipschitzian behavior in subspace. Yeah, exactly, a domain. And not maybe release this constraint for some particular samples. Yeah.
Thank you. So thank you. I will just go with a concluding remark. So what we've shown today is only one small part of what we do. It was aligned to the first perimeter of the standard, which is supervised machine learning. But also we are developing trustworthy AI methods for other parts of AI capabilities, especially planning and scheduling, more generally decision-making. So or you provide elements for explainability of the planning, or you provide robustness for a planning task. So it's also something on which you can connect to us. And I'm quite sure for Fly AI Forum next year, we'll also showcase all the stuff which are linked to decision-making. And also we start to work on Gen AI, trustworthy AI tools for Gen AI, or we can better understand embeddings of which are performed by large language model, for example, to provide some level of explainability, or we develop metrics, confidence level that really are good confidence that you can rely on for Gen AI applications. So all of that is in the making. And so stay tuned. We'll present that soon, or you can connect to us if you want to get acknowledged with these tools. One more time, all of that is available to the community, so you can test them, you can provide us feedback, and you can also contribute. Also, there is a call, a Cesar call, which is coming on the development of future regulatory framework for digital European sky. It's one of the ongoing Cesar call. And of course, since there are requirements in terms of developing trustworthy AI methods in this call, we will play a role there, and we are happy to discuss with any of you, also potentially on collaboration linked to this call. And thank you very much for your attendance. And I think we are to resume in the main room. Thank you.